want you to know Riemann sum first if you want to understand volumes better. I believe we went over this case already, but why not? Let's do it again. 4, 0, 2, x, y. What is that function? Y equals 4. That's my function. That is f of x. Good so far. Do I need calculus to find this area? No. I'm sure you know the answer already. What is the answer? 8. Then times with great. Function y, so f of x dx from a to b, great, all the facets fine. When you first learn integrals, they are antiderivatives, but people sort of realize, oh, when we find the integral, this is what we're finding. I can find the area under the curve multiple ways. One simple way would be to say, divide it into 4 equal parts. Good? So 1/2, 1, 1/2, 3/2. Good? Find the area of each piece, add them all together. Agreed? Will I get a different answer? No. Let's take it one step further. Equal parts. Find the area of each single piece, and then add them all together. Will I get a different answer? No. The next logical thing to do would be divide it again over and over and over. So if I have to split this into pieces, how many possible pieces can I think of? Infinitely many, do you agree? But hypothetically speaking, equal width, yes. And let's just say I have n of them. Last class, I believe I showed you the strip, the rectangular strip. There is that strip, okay? Even though one of 8 pieces, in an arbitrary way, that is delta x. Good? So the width over here is delta x. What is the height? If you bring that delta x closer and closer and closer, make it as thin as possible. With me, what would the height be?
4.
4. Isn't 4 f of x? Yes, no, maybe. Agree. So f of xi at some point, 1 point, 1 line, extremely thin rectangle, infinitely many rectangles, add them all together to find the area. In math, infinitely many, what do we do? We can't realize infinity technically, but theoretically we can get there. What did we use in calculus 1? Limit, very good. So I'm going to sum over all pieces and take the limit. Good. In simple terms, all of that becomes that. infinitesimally speaking. Infinitely many points would simply mean a continuous function. That would become this. Infinitely small change, uppercase delta, becomes d. So, well, I'm running out of shapes. Delta x, when you apply the limit, becomes dx. That is the definition of an integral. Good. Do we follow? Okay. We have to extend this idea to get volume. Dimensional measures, did we take physics? No, Lorenzo is taking physics. In one dimension, what do we measure, Lorenzo? In one dimension, if you're going to make a measurement, what are you measuring? Others should know too. Right? Very good, Xavier. No, agreed. 2 dimensions. Think of this floor. Length times width, that has a name.
Area.
Area, great. 3 dimensions. Whatever that's filled in here, volume, good. Good so far. Okay. In order to find the area, what I pretty much did is I took infinitely many thin rectangles, put them all together. Agreed? Got that? If I want to find the volume of this classroom, is it reasonable for me to say paper as thin as this? Stack them, not this size, but one that fits the size of this room, going to stack those thin papers, sheets of paper, all the way up to the ceiling. Add all of their areas. Would I get the volume? Yes. Xavier, do you think yes? Why? It just makes sense.
Yeah, I guess so. You have the, well, they're all like a thin piece of volume. So then when you put them together, you get to a larger volume.
So area is an infinitesimally thin volume. If you took a cube, and imagine you have a cube, you squished it, and you have a very thin cube, just like you have a thin rectangle. Same concept extended to another dimension. If you have difficulties understanding or visualizing this, putting sheets of paper all the way up to the ceiling, if you can't have gluten, you may not like this example, but who likes bread? Sliced bread. Okay, now when you go to the store, what brand do you like, Kristen? What brand? Doesn't matter.
I don't really know.
Organic, preferably.
Huh?
Any brand that's organic.
Okay, any brand that's organic, okay. I'm going to go for a nicely shaped loaf of bread. Let's say a pack of Wonder Bread. Good? Yes? So it's a huge block. Agreed. Now, it's sliced bread. If I took all the slices apart and then put them together, would I get the same volume of bread? You're not eating, you're just stacking them back. Same volume, yes? The slice of bread is this thin sheet. You're stacking slices to get the full bread. Good? Organic calculus. I'll have to come up with a gluten-free example. Someday I will. Technically, paper is. Do we follow?
Yes.
Stacking? Okay. Based on the logic, how would you change that expression? to say, get a volume.
Would we add change delta y? Would we add delta y?
Another way, but we're not doing multivariate calculus here. We're going to keep it simple. Yes. This way. Okay. Got myself a nice little cube. Good. This room, but regularly shaped. Zero, two, 2 outside, 2. What is the volume of this? 8, 2 times 2 times 2, 2 cubed, 8. Okay. Now, thin sheet, yes? What is the area of that sheet?
4.
4, yes? I'm going to infinitely stack sheets from 0 all the way up to 2. Good? So, infinitely many. So when I add them together, I'll get a volume of 4 times 2. Agreed? Yes? That said, how would the notation change when you write over here? In this case, just the height defined by the function, integrated a to b, you got the area. My question now is, if I want to find a volume, I am summing up the areas. Very good, Xavier. The areas. When you go to calculus 3, you'll be summing up volumes. So what happens in 2, 3 dimensions can be extended to n dimensions. This is all we can realize visually. So whatever we did with this, using one reduced dimension, you had a length. Over here, A to B, 3-dimensional volume. Go one step down, you have area. Good. Multiply that by chords. What's she going?
Taking the height.
Which is using this notation. I've got a of x, this has to be. The other part is the integral, what goes there? 2 letters. Good. You might wonder, well, this guy was talking about strip, strip, strip. What is that? Where is it coming from? Caleb said the height. What is this height he is referring to? Thin slice of bread. Yes? Length times width would be the area. The thickness right here is simply the height. Area multiplied by height, volume. Good? Easier way to remember. Volume of a cube, length times width times height. Yes? But what is length times width?
Area.
Area times height. Height. That's what we have there. Good? We're just extending it to infinitely many slices. Follow? Okay. This is one case, but what if you have a situation where you don't have a nice shape such as this, rather you end up having something like that. That is not a 3D shape. We want to get a 3D shape. If you have just a curve, you can get a solid out of it by spinning. Have you ever seen how clay pots are made? Have you ever seen clay pots? Right? They rotate and raise the clay. Pretty much spinning forms a surface. If something forms a surface, inside it, you have volume. Agreed? Clay pot and, the person's, crafting that clay pot, as it raises, via spinning, you end up getting a hollow space. That's the volume, correct? Same logic. If I have a curve, I'm just going to spin this. I can either spin it with respect to x-axis or spin it with respect to y-axis. Let's say I spin with respect to y. That is the shape I'll get. Do you agree? At the end of the day, it's going to be a hollow pot of some sort. Yes? If I took this red line and I spin it, what will I get? That's okay. A cone. Can you visualize? How do you make a cone? Have you ever done it when you were young? Sheet of paper, cone. You revolve it and stick it with tape to form a cone. Same logic. Good? The next time you get ice cream in a cone, think of calculus.